Last but not least, we now turn to the final pilot of the first implementation, and who is led by our hosts, actually. The secure information in cross-border data spaces, which addresses one of the most critical challenges in the digital era, ensuring trust and security in the exchange of cross-border information, something that is critical for interoperability. The solution developed incorporates advanced technologies such as post-quantum cryptography and data spaces grounded, and I think you've heard this a million times today, the once-only technical system. That is a real example of the once-only principle. Let's welcome our colleagues and hosts, Lante Gorka, to the stage for the final demo of SGA1. The floor is yours, Gorka.
Thank you, Alex, and thank you, everyone, for standing till the last moment. So this is the last, as yesterday, the last talk before the lunch. So you have to stay a little bit, and then we'll go. Let's make it as short as possible. So pilot 1, okay, secure information in cross-border data spaces. The title is very ample. We could go many ways, but we knew that we wanted to do something technologically different. And we are into quantum technology, so we knew that quantum cryptography could play a role there. So how did we do it? Let's guide you through the process. This is the agenda. Let's talk about the 2 years of work, the use cases we started with, and what we finally ended with. The security framework, a small demo, and a recap. So pilot 1, you can see 3 organizations here, GRNet, Greece, DNUM, France, and Biscay Atlantic, the 3 of us. 3 organizations with different profiles, but also with different roles. Atlantic provided technological grounds, while GRNet and DNUM provided all the business model and business cases. Also, GRNet had a lot to do on the OTS, the data spaces ground that we used. So here's the team in a map. We continue. And which ones were the overall objectives of our pilot? We only had one. Was to implement a proof of concept, okay? We knew we were dealing with cryptography technology that's very new. We didn't know if it was going to work. So we wanted to try it, test it, and see if it was going to be feasible. So implement a proof of concept for a commonly agreed cross-border use case, where security and privacy was important for data exchange of sensitive information. That was our goal. So see if we can do it. So next was to decide where to implement those principles, those 2 principles, data sharing and security. We found 2 use cases, a skills use case, which was provided from GRNet, and health use case, which was provided by DNUM. As you will see later, the health use case, initially, we worked on it for over a year and a half, and then it was dropped. We changed, and it was dropped again. So we ended only with 1 use case. But it's OK, because we managed to prove both things, sharing data and doing it securely with post-quantum cryptography. Here are the 4 technological points, 2 families, security, and data sharing. You will see that later a bit more. This is a boring chart of the first year that says we prepared to do the things. And this is another boring chart of the second year that says we did the things, mostly in many, many points, control points gathering together. I think someone in some of the pilots said earlier that's important to meet face-to-face. We did 2 control points that were really relevant. Now better. Okay? Yeah? Thank you. So we did 2 control points that were really relevant for us, because we met in person, first in Athens, then in Paris, and we advanced a lot in our work. So it's important to meet with people not only on Zoom, on Teams, face-to-face. And the final control point here, when we ended everything. Okay? So this is the second part, the second year of our pilot. Let's talk about the health use case. Secure information in cross-border data spaces. So what did we want to do in health use case? France came with a problem. They had many hospitals, many clinical medical facilities that were not really connected. They didn't share information. So when a patient went to somewhere, they had to file over email, over WhatsApp, send all the documentation, which was not secure, which was not centralized, it was difficult to know what was going on. So they said, we can use an instant messaging app that's centralized, and we can take the patient data from a data space, kind of aggregate all the data, and we can share that to professionals so they can give a better service. That looked nice, so we started working on that application based on open source metrics protocol, and an application that was built on top was TCHAP. TCHAP is also an application that France uses internally for public servant communication. This was going to be a different version of this application that met health standards, but it was discarded. Okay? This is a diagram of what we wanted to do with all the extended connectors for the data spaces and blah, blah, blah. But this application, in October of 2024, the French government said, we don't have funding, we don't have priorities for this, we are going to move on to something else, so this got stopped. So what did we do? We tried to apply the principles that we have here in someone else. So France had also a file transfer application, so we said, why don't we do our data spaces part with the file transfer application? If you want to send something from some ministry to another ministry, let's have a way to aggregate data instead of consulting many different databases or systems. So we proposed this other diagram and schema, but this arrived too late. It was around February, March this year. We didn't have enough time to implement it. So we didn't want to risk the skills use case, which was the one that was working well and was going to be finished. So we decided to stop this part and focus on the other part and deliver. And we did deliver. So the skills use case. You will see much in detail later because Gernet is going to be on a stage explaining in detail the case, but it's basically is a student that moves from one country to another and wants to study, apply for a degree, a diploma, whatever. And then he needs to provide certificates from the origin country, the original country. So if you want to study in Greece and you come from France, you need to provide your diplomas from the university. So you can either have them, scan them, upload them, or enter in an interminable hassle of bureaucracy to get those things going on. But with the portal Study in Greece and the OTS system, which is this one, that was feasible. Okay? I'm going to explain a bit more about the OTS later. So what we said is, the one's only technical system is the European Union standard. If I'm not mistaken, no, it's not here. Okay, we'll get to that later. It's a European Union standard that provides government-to-government information exchange. That's defined, that's working. So we decided to put an encryption layer on top of that, because information travels in an unsecure way, because they are assuming that the networks are secure by default, which is not always true. So we decided to use what was going on in that Greek procedure portal for the diploma exchange and add security on both sides. As we had the experience of what happened with the health use case that was dropped mid-development, or nearly the end of the development, we thought it was interesting to get some commitment from the participants. So from the study in Greece, we asked them to sign a letter of intent saying, yes, we are going to commit to the project, we're going to do this and that. So it was difficult for them to back off. They could, but at least they have a letter signed, so that makes much more difficult to get on. So they also provided the diploma specimen for the application to work, so we had everything, and it went very, very well. And going to France, we needed the French counterpart. We found 2 universities willing to participate, Université de Lille and Sciences Po, with many different campuses. So Université de Lille contacted and agreed, sent the letter of intent, signed the diploma, and Sciences Po, yes, we are on it, yeah, we are on it, yes, we are on it, yes, we are not on it. So we also lost that one. So as you can see, the road of innovation is full of lessons learned and things that happen in a different way as you expected. But we managed to get 2 universities, 1 on each side. We managed to get technology working. So it all went well. Let's talk a bit about the technology, because later my colleague Iker will go on stage to talk about the security framework, which I think is our masterpiece because it's going on the second SGA too. So we have these points. A security framework that uses post-quantum cryptography, which allows secure exchange of information between 2 points, 2 servers, and is resistant to quantum computing attacks. The second one is the fully homomorphic encryption. That's encryption that allows data to be treated and used without knowing what's inside. I mean, you can give a number to an external provider. They can make calculations, give the calculations back, but they don't know what's the original information there. So that is used to train AI models, for example, to get information for medical diagnosis or systems. And the points 3 and 4 were the data-related points. The data framework with the once-only technical system that Gernet knew, had the expertise and developed, and the data framework that finally was discarded but documented. So here is, now yes, this is the slide, the once only technical system. If it's should be on your radar because it's very interesting, it's the first EU-wide cross-sectorial and cross-domain data space. So this is European Union standard. And it's used for secure government-to-government data exchange. So it's designed in a way that there are many servers, many layers, many different, let's say, identity providers, evidence providers, receivers, requesters. So everything is defined. So you just have to plug the right components, and your system could be on it. So going on, the security framework, which is our centerpiece. Secure encryption algorithms. Why? Because quantum computers can break current technologies of encryption. Maybe not now, but in a few years, because it's a question of having the right amount of, let's say, the right algorithms that provide the mathematical capability. So quantum-safe encryption algorithms are algorithms that run on traditional machines, the ones we have now, but you can use those to protect against those computers, quantum computers, and then work with encrypted data. Information we know is stolen every day. You get phishing, you get hacking, you get attacks. So if information is encrypted and you never unencrypt it, you work with information as it is encrypted, it's safe. Even if it's taken out, it's safe. So that's the homomorphic algorithms where they appear. So we prepared a framework which is language agnostic. It's a Docker container that has everything. It can run on any server. It can be called via API, and it was integrated with the OTS system and all the modules, the PQC and the FHE. These modules that you can see here are open source libraries. Okay? We based our development on open source libraries. Initially, when we started the project, we thought that we had to, or maybe we had to at some point, buy IP proprietary libraries, because we had identified some. But at the end, we found, and Iker will explain the roadmap very, very shortly, we found open source solutions that were compatible with the highest standards. This is a framework more in detail with all the APIs and calls, which I'm sure you will like a lot. And I think it's a moment for Iker to jump on the stage and talk a little bit more about the security framework. Iker.
Hello, everyone. My name is Iker, and for the next minutes, I'm going to talk about post-quantum cryptography. You've just heard Gorka explain the fundamentals, so now we are going to take the next step and go deeper. So we're going to get a little technical, but don't panic. We are going to go through quantum-safe cryptography and why we need it, and then we are going to explain you or introduce the software tool we've developed, the security framework. So as the quantum computer rises, quantum computing, we had the power to run new type of algorithms. There are two main algorithms that are the enemies of traditional cryptography. We'll have to keep an eye on it. There's the Grover's algorithm. This algorithm speeds up searches. So if we get encrypted data and we have to evaluate, imagine an attacker has to evaluate all the possible keys for finding the correct solution in order to decrypt the messages. Grover's algorithm will speed up that amount of time in a quadratic way. Imagine it will take millions of years. This algorithm will speed up that process a square root of that millions of years. That is still a large amount of time. With the standard keys we use nowadays, this is not a threat. We are safe against this. But we'll have to keep an eye on it in keys that don't maybe standards or systems that don't use these standards. The short algorithm, in the other hand, is the big algorithm we have to take account. And you may know the algorithm RSA. That is the main algorithm, the hard algorithm we use to get safe communications nowadays. The strength of RSA relies on factorizing large numbers. And this algorithm is known that it completely breaks. It allows us to factorize that large prime numbers and allows us get the information in the decrypted messages and breaks traditional cryptography. So this is the main enemy, but don't panic. We still don't have the capacity with quantum computers to break this, but it's a matter of time. So we have to protect ourselves, and in 2016, the NIST made a call. The NIST is the National Institute of Standards and Technology, a US government, and made a call worldwide to researchers, government institutes, to develop new algorithms, maths against these quantum computers. And it's a process that is still ongoing, but in August 2024, last year, 4 new algorithms were standardized and formed the base of PQC that in the future we're going to use them to implement this new technology, quantum safe technology. The 4 algorithms are Kyber, Dilithium, Falcon, and Sphinx. They have different purposes. Kyber is for key exchangement. Dilithium, Falcon, and Sphinx are for digital signatures. But in 2025, this year, in March, another 5th algorithm was proposed to be a standard, a backup for Kyber, that is HQC. So with this, we have like the basis, we have the new technology that we can implement in order to get secure communication, in order to be cryptographic safe. So the maths behind these new algorithms, the only thing you have to know here is that this technology don't rely on factorizing large prime numbers, rely on a set of linear equations. You may think that all of us studied to solve this equation in high school, but it comes with a little change that in the independent term is added like a small random noise that make really, really difficult to solve these equations, even for quantum computers. Okay, so as Gorka said, we have 2 systems to get quantum safe, quantum secure. In communication, one was PQC, and this is FHE, fully homomorphic encryption. And as PQC is intended to be general purpose, this one is for specific user cases when we have to operate in encrypted data. Imagine you have an AI model that you want to train with sensible data, maybe medical data. And you can do it if your model implements FHE with that data encrypted. You don't have to decrypt that data for using it. This is the power of FHE. So it's time to talk about the software tool we've developed. This relies on 2 main libraries. Is the OQS library that is really, really aligned and updated with the NIST standardization. So it's used by everyone, by all the community to implement PQC. And we have the OpenFHE library that is used by researchers and by academics in the topic to implement FHE. So these are really, really solid roots for our security framework to work on. So as Gorka said, the framework is packed in a container package that has all the requirements needed by the software to run. And when you run it in your computer, you could run it in any operating system. It's agnostic to operating systems. And when you run it in your computer, it will expose an API. You see there all the functionalities, all the methods you could call in the API. You could decrypt. You could encrypt messages, you could sign documents, verify signs, and also you could do all the operations we mentioned before with FHE. This is a really, really flexible tool and modular, so you can use it everywhere. Also, we did like a user interface. And with the functionalities packed this is for key management only. You can generate pairs, like store keys from another people. You could see in the files and directories, and also you could run tests in the backend to ensure the correct functioning in your computer. So that's it. Thank you all for listening. And Dimitris will do the spin-out, sorry. We'll talk about the use case.
Thank you. So bear with us just a few more minutes, and then we can have lunch. So, as Gorka and Iker already explained, this pilot was developed just to highlight how. Not this pilot. This use case was developed just to highlight how we can successfully integrate the security framework that Landic has implemented into an actual real-life scenario. So as Gorka already explained, we had 2 use cases we started with. Health use case was dropped, so we stayed with the skills use case. So the idea is that we have a student that wants to apply to a Greek or a French university or vice versa. And in the scenario that Dimitris will showcase in a minute, we have someone who wants to apply to a Greek university, and they need to attach some evidence, they call them. So evidence could be a degree, a certificate, something that from a French university to their application form. And we did that by using post-quantum secure and authenticated data transfer via OTS. So the second part that Iker just showed, where is Iker? I lost him. Oh, here, sorry. About the fully homomorphic encryption, we did that because we need some data that the user might provide to be also fully encrypted. So because we might not trust, the cloud server that we store everything. And I'm not a technical person, but if I've got everything right, that means I understood what we did in this pilot. So thank you so much. What's important, I think, in this pilot is that the scope of the scenario can be extended to any relevant situation of cross-border data sharing for citizen data with public authorities via the OTAs. So I think we also went beyond the scope, like we did a proof of concept of how this could work, but this can be extended practically everywhere. So why this is important? This is a real need that we had in the use case. We have students increasingly apply to universities abroad, and the problem is not to how we can exchange documents. I think we have done that before already, but how we can do that in a very secure and a future-proof way. So classical encryption won't withstand quantum threats. I don't want to talk more about quantum. I think there are more experts here that I have talked yesterday and today about that. But the goal was to build a secure GDPR-compliant and quantum-resilient digital service. And I already went through the overview of their case, so I don't want to stay here. The challenges were security, privacy, and interoperability, which we talked a lot about today. So, as already explained, we use the 2 core frameworks, the security framework by Lightning and the data framework based on the OTS. Our role was to implement and test this in a live proof of concept. Dimitris will showcase more about that. This is the I think you've already seen this diagram already before. What we have introduced in the last couple of months is that we have the security framework also in the provider and not only on the procedure portal. So the objectives, I think I've already gone through that. I know it's like last presentation before lunch, so I'm not going to stay here a lot. So what were the key outcomes is that we proved the feasibility of post-quantum and fully homomorphic encryption tech in public services. We have the simulated cross-border data exchange between France and Greece. Again, this was the partners that were involved in the pilot. This can be done to any, it's not limited between France and Greece, obviously. We have secured user privacy via encrypted cloud computations. And because this was a successful integration, we decided we're going to use this framework in the next SGA, actually in 2 pilots. So you're going to hear more about that in the future. And I will now give the floor to Dimitris to showcase the demo of what we did.
Can I be heard from here? Test. Okay. Hello, everyone. My name is Dimitris Masad. I'm a full-stack engineer at GRNet, and I will be demoing our proof of concept built on top of the once-only principle using the OTS once-only technical system building blocks, alongside with the need to have the authentication of European citizens, and of course, the security framework to guarantee the encryption of the data. So I will go back to our pilot. First thing that I need to say is that the once-only technical system relies on the authentication of the user using the EIDAS system. Of course, setting up EIDAS nodes or using the production EIDAS nodes was not an option for the proof of concept, was outside of the context of the pilot. So what I'm going to showcase to you is basically a local login with a test user, but of course our authentication system already has implemented, let's say, the EIDAS modules, so that if we were to go on production, we could do this by connecting our system to the actual Greek or French EIDAS nodes. So our building blocks do actually have the necessary extensions, let's say, to do this. Now, going back, our user is a French citizen that will authenticate to our Greek website. Our platform is studying Greece. The French citizen basically wants to apply to a Greek university, and the platform will request from him to give some of his details, fill an application, let's say, that will be, in a second step, will need to be reviewed by a manager. So here we can see the user is Jane Doe, and he's called to basically create the application and fill it. So we can press this button, and now we can see that the user, we have this form, and the user needs to fill all the necessary data. What you see is some of the fields are blacked out, and this is because EIDAS would provide this data. And if we go a bit lower, we will see that one of the fields required is an evidence. Now, the user, of course, has the ability to upload a PDF or to actually use OTS and retrieve it online. Now, I will pause from the demo to explain a little bit about OTS and what are the building blocks that OTS works on. Basically, each country has their own Domibus node, and the Domibus is a software created by the European Union that is used in multiple European projects. And the idea is that it's the transport layer between the requests and the responses from each country. So what we have done on our proof of concept, because we, as you can understand, we need to isolate the environment so that we can test with it, play with the encryption of the data, so that we, alongside with Dinum, France, we created two isolated Domibus nodes and connected them together. And we have this system right now that only has, let's say, a virtual Domibus network that only consists of these two nodes that communicate with each other. Now, one other building block of once-only technical system is actually the common services, which is the way that each country can query which evidences are provided by which countries and which requirements, let's say, each evidence can fulfill. So if we go here, we will see the user just selected to retrieve their evidence online, and the first thing that they need to select is on which country is the evidence located. So on our use case, France is the country that the evidence should be retrieved from. And now we can see that our system knows that from France we can retrieve a bachelor's degree certificate to be used on the requirement of proof of enrollment in tertiary education institution. So if we go back here, we will see that we can select France. There is only one option, so we will use the bachelor's degree. And then we see which are the providers from the French side that actually provide this evidence. And the user, of course, will select the Education Ministry. It's the only option. Now, going to the cryptography options. On the OTS system, the user may select to preview their own evidence or basically not to, and directly, if the provider allows it, it would retrieve automatically the evidence. I don't want to go in too much detail on the once-only technical system because we don't have a lot of time, and I don't want to keep you away from your food. So I will go ahead on speaking about PQC. Basically, what we have here is, alongside with the two Domibus nodes, we have the Greek side that also has the application. This is the application that we are seeing, and the French side, which acts as a procedure porter or the OTS evidence requester. From the other side, we have the French Domibus node that has an application connected to it, which is the French evidence provider. Now, both of these systems have a security framework installed alongside to them. And basically, we have generated some keys, some post-quantum keys, and exchanged them over the network. So when we see this option, basically, the system has already checked if the French side is added to the Greek system, and so whether or not the post-quantum cryptography is available. If it wasn't available, this option would be grayed out, and it will let us know that PQC is not available. The user would select that they want to use PQC. Of course, this is to demonstrate it because in a real-world scenario, when we would use PQC, we wouldn't need the user to know about it. This is the thing, that the cryptography is on the transport layer. The user doesn't need to know about it, and he doesn't really care, let's say. It doesn't affect the UI UX experience. So going to the next step, here we can review the request that it is about to be submitted. And once we press submit, our system will basically submit the Domibus message. The actual request has been encrypted. And now we are waiting for the French side to respond to our system. It will take a couple of seconds if everything works correctly. All right. So the user has just received the message that to proceed, the evidence provider requires you to re-authenticate. So basically, the French side just gave us a link, a URL, that it told us to, OK, provide this URL to the user and send the user to our site so they can authenticate, and we can make sure that they are who they are, and they can select which evidence should be transmitted back. So by pressing continue, we will see that we will change, we should be logged out. Let me simulate this. So we are now on the provider side, and the user, the French side also requires the user to be authenticated in the same matter. We would have the IDAS options here, but as I told you, we are simulating and we are using local logins, so the user can also authenticate from this side. And once we are in, we are now on the evidence provider side, where the request has been received. The available degrees, the available evidences, let's say, are being shown to the user. The user is able to preview them. This is the test certificate from the University of Lille. And actually, there are two options. One is in English and one is in French. The user, other than the preview, can, of course, download them, can cancel the request, or select which evidence wants to send back to the Greek side, and press send. Now, when this finished, we were redirected back to the Greek side, so we are requested to re-authenticate, and we are back to on our form. Now, a small change here. If you can see, instead of having the option to upload an evidence, there is already an evidence received from the system. Behind the scenes, Domibus, from the provider side, received the action from the user that they want to send this evidence, encrypted the message using post-quantum cryptography, and send it back to the Greek side. The Greek side was able to receive the message through Domibus, decrypt the contents, see the actual evidence, and store it to the system. Of course, we can verify that the correct handling of the evidence has been done. Let's say that we will download this. Yes, let's replace it. And we can open it and see that is the actual evidence that we saw from the French side. Moving on, now the user, okay, we just see how the PQC is implemented inside OTS, inside an actual use case of a public sector service. Now, we will move on to the FHE, the fully homomorphic encryption part of the integration, which is actually, once the form has been submitted, we have collected some sensitive data from the user. Now, the assumption is that we want to outsource some of the operations in order to validate whether the form should be, let's say, does fulfill some criteria or not. And we can assume that this is a heavy calculation. And instead of running it local, we want to outsource it to a cloud provider that we don't trust. And because we don't trust them, we don't want them to receive sensitive users' info and have them, and it poses the risk. Instead, we will use the fully homomorphic encryption from the security framework, and we will encrypt the data, we will transform it to vectors. The cloud provider will receive these vectors, they will run the calculations, they will have the output without even knowing the actual data, and they will send it back to our system, and we, from our side, we will be able to decrypt them and know exactly what's the output. So I will be as fast as possible to fill this form. Let's say France, let's say test, let's put a number here, let's say Paris, France, and the family income of, let's say, this. Now, we can save the form and submit it for approval. Now, once we have submitted it, we are done as the citizen, and we need to log into the system using the manager account so that we can see how the manager interacts with the system. So here we are as manager now. We see all the submitted forms. We see the form that we have just created and submitted as citizen. We can go in and see, okay, all the details that was submitted. And there is this button, this validate button. Now, when I press it, we will simply see some results. Under the hood, what will happen is what I explained before. We will take the family income and we will encrypt it alongside with the date of birth. The idea is that we want to simulate the need, let's say, for the validation that I described before, and to make sure that the citizen that is applying is making less than X amount of, as a family income per year, and is at least 18 years old. So these calculations will not happen locally. They will, we will encrypt the data using the security framework. We will transmit the data to the cloud provider service, and we will get the results back, hopefully. And all right. So as we can see here, we have one validation that passed, which is, can you see it? Yes, okay. Which is the true part, which is the date of birth. Our user is at least 18 years old. And the second one was the fact that the family income exceeds 10,000 that we have. So these simple calculations, they don't need to be simple. We have them simple just to showcase the actual usage. But it could be anything, and the cloud provider side did not know the actual data. It only had some vectors. This is very important because this means that we can protect our data, protect citizens' data, and have the ability to have a lot of resources, let's say, to run many calculations for many services without worrying that the cloud provider, each cloud provider could, let's say, leak some data to their logs or whatever. This is our demo, and thank you for your time. And I think, Gorka, you can come and do the recap. Thank you.
Thank you, Dimitris. Very interesting to see things working in real world. As Dimitris said, There were simple things that we tested, but we wanted to make sure that the encryption algorithms and the calculations were be able to be performed. So we tested, and it works everything perfectly. So let's do a brief recap before ending this pilot one, and then in the morning sessions, then we'll have 1 hour, 1 hour and a half of lunch and networking pinchos, so you can enjoy each other. So the recap. First, let's talk about risk management, okay? You saw some of the risks we had in the project and how we managed them. So I'm going to start with the lowest risk. This is low risk now, because it's working. It was not low risk when we started. It took 2 years to do this project, but we started, as you know, European projects start earlier. So we kind of presented the concept 1 year earlier. So 3 years ago, we said we were going to do something with quantum cryptography. We were a bit crazy because we didn't know if it was possible or not. Technology was not advanced. You saw the NIST algorithms in 2016, but it's still in process, and we're not finished in October 2024. So we could have guessed right or wrong. But that's why we encapsulated everything in a security framework, in a framework that could be changed. So you could still call the same functions, you could still use the same functionality, and if things change behind, you can change them. You have the possibility. So that was our risk management. We went for a new technology that we thought it was going to work, and that we encapsulated in some framework that would do all the, let's say, dirty job. So that was the risk and the management. The medium management was a timely on board of universities, in this case, French universities. We approached them with not much time because there was some constraints there with the health use case. So we managed to get one of the universities. We didn't manage to get the other one. So to be safe, what we did was sign a letter of intention, declaration of intentions that you're going to do something with us. You're going to put all the resources that are needed. Okay? So it went well in one case. It didn't go well in the other case. But that was the risk and the management that we had to do. And the final one, the biggest risk, as you saw, was a use case that was we have been worked on it for nearly a year and a half, was dropped. So institutional support and political buy-in. It also appeared on some of the other interoperability policy-making talks. You need to have the right political support and buy-in. You have to be careful with government changes, priority changes, budget changes. So when projects run for a long time, you have many problems. So you have to try to do those. You have to get the commitment. You have to get people to sign things or, I don't know, reserve budget. It's not easy to get this, okay? France didn't get the buy-in, but we had 2 cases, so also have a backup plan. That's also a good option. Don't bet everything on one thing. Try to have a backup plan. So these were our biggest risks. These are how we manage them. And what did we get from here? Well, reusable blocks. SGA1 is ending today. Not today, the end of the month. We have to send all the documentation. But it's ending this month. And we'll start with SGA2. So we had reusable blocks, as you saw in Pilot 3 and Pilot 2, the definition contest, the rules as a code. There are many blocks that are going to be used on pilots of SGA2. So security framework is being used on Pilot 7 and Pilot 8, AI, automatic evidence processing, and citizen-centric rules as a code. We are going to use security framework there. We still don't know how, because we haven't defined the full extent of those pilots. We'll be working on them, but we know there's going to be data exchange. We know systems will have to talk. So there is we're going to implement extra layers of security. We will work on that. So we have a framework that has post-quantum cryptography and fully homomorphic encryption capabilities, is independent in a Docker container, as my colleagues explained, based on open source libraries, which means costless, and is ready to be expanded and improved on SGA2. So that's the road we have ahead. We learned, we succeeded, and now let's move on to the next stage. So that was all on our side. Thank you very much for listening, and thank you for coming to this morning session.